The last technique that we'll explore in assessing the normality of sample data, in this chapter at least, is the creation of what we call normal QQ plots. Q stands for what we call quantiles, which is another word for percentile. Quantiles are slightly more versatile in that we are talking about any proportion from 0 to 1, whereas a percentile is specifically all the whole number percentages, but the difference is minimal in that we are still talking about, we are looking at data values for which X% of the data or of the set lie below this value. So the 50th percentile, or the median, means that 50% of your data values in this set are below this value. What the QQ plot does is it plots points that are paired, x comma y, where the x value, or the first number in the pair, is the theoretical quantile. So in other words, the percentile that corresponds to the z distribution, the standard normal distribution. Hence why we have on the x-axis values between -2 and 2. And for the second value in this pair, then we are looking at the sample percentiles. You may think of these as comparing critical values to critical values. Now, if these line up in some sense, so in other words, if the scatter plot of these points is approximately a straight line, then we'd say that we have strong evidence of normality in this sample data set. If they don't, or if there's some very clear trend where the data values are, for instance, if we were looking at a different normal QQ plot, and we had the theoretical percentiles of the standard normal distribution, and we were looking at the percentiles of some other random sample, if they follow a trend that's more, that curves away, specifically as we're looking at this straight line, then that's evidence of other kinds of patterns. And the only pattern that we're looking for in order to be sure that we have a normal distribution is the straight line pattern. And in fact, something like this might indicate something more along the lines of a uniform distribution. Why might that be? So remember that the quantiles of a standard normal distribution, they lie between 2, -1, 0, 1, and 2, but these are telling us something about the location of the data as well, right? So between -1 and 1, we said we have about 68% of the data, and 0 gives us the 50th percentile. So here's the 50th percentile is roughly, but is exactly there. And if we have between -1 and 1, 68%, then that means above we have 34%, and below we have 34%. In other words, at -1, we're actually looking at the 26th percentile, and at 1, we're looking at the 84th percentile. And we can do some similar things to figure out what will be the case for 2 and -2, -3, and 3, or we can similarly figure out what the corresponding percentile would be. Now, for a uniform distribution, on the other hand, because of the percentiles being uniformly distributed between the lowest value and the highest value, these are not going to match in the middle, because if they did, we'd be looking at something along the lines of, if this is the 50th, then maybe this would be the 30th, and this would be the 70th, 90th. They'd have to be uniformly distributed. Does that make sense? So 20% between that, 20% between that, 20% between that. But these don't line up directly because 26% is there, 84% is there, and then so unless they're straight lineups, then we don't have a normal distribution. This is much more complicated of a diagram than we're actually going to be using. Really, the importance is, does it match this straight line? But you can use some argument like this to make sense of what we're talking about when we mean, how do the quantiles line up for the normal distribution and our sample data set? In a future video, corresponding to a much later chapter, we're going to be talking about the goodness of fit technique. So the goodness of fit actually falls into a subdiscipline of statistics where we are performing inference tests. And this will be we will be connecting all of the techniques that we looked at so far in terms of what this is saying about the goodness of fit of the normal probability model to our sample data set.